Rock and roll. It's the bottom of the ninth. The score is tied. It's time for the big one. All right, guys. So now what we're looking at is a good example of how all the concepts within our introduction to conservation of power, to how we can actually do power factor correction and actually create efficiency within our system. Now we actually have a problem where we're basically combining all of that together into essentially one holistic analysis. So one of the problems that was in chapter 11 is that we took a look at 11.69. And so for this one, we had basically, once again, a source that was in parallel with a resistive inductive load. And just by knowing that, we know that we're going to have basically positive reactive power within the system. That's going to cause an offset of basically an apparent power that's going to be way greater than basically the real power itself. And so in this case, guys, what we're going to want to do is put a capacitor in parallel with that to actually correct basically that reactive power and actually essentially have a negation effect, to which most of what we see as far as the real power within the system is all going to be absorbed within basically the resistor of the system, and therefore we actually will create efficiency and then ensure that we are actually producing the smallest amplitude of instantaneous power to get the most real power within the system. And there's a lot of benefit for this. Power companies like this because it means that they don't have to produce as much essentially complex power to deliver the same amount of real power. So in this case, we have 440 at an angle of 0 degrees RMS with 377 radians per second. And now we're actually going to determine what the power factor is, because the power factor tells us again that efficiency within our system, and it tells us how far do we actually need to start correcting. So let's take a look. So the first thing we wanted to do in this problem was go through and calculate the complex power from the source. So for here we had VRMS, the magnitude of that squared, divided by Z conjugate. And so that's 440 squared over 20 minus J15, because remember with the minus sign here, that's Z conjugate. So Z conjugate of 20 plus J15 is 20 minus J15. And what we get out of that, guys, is 6,200 watts plus J4650 volt amperes, or essentially 7.7 at an angle of 36.87 kilovolt amperes. Okay? So we can automatically look at this and say, oh, well, the system's definitely not efficient. We got too much inductance in the system. We need to actually correct that. And let's see if we can create a negation effect by putting that capacitor in parallel. And by doing that, obviously, we don't change the voltage across the load, nor do we change the current that's actually being delivered to that load itself. So the power factor, if you remember, we can calculate that one of two ways, just by taking the cosine of our phase angle of 36.87 degrees, or just basically taking the real power, or average power, divided by the apparent power, which is just the magnitude of the complex power. So cosine of 36.87 degrees is equal to, at the same time, 6,200 over 7740. And oof, guys, I know for some of you, you may be thinking, oh, 0.8 is not that bad. I mean, that's essentially a B on a test. 0.8, and that's not good efficiency. That's pretty bad. In fact, actually, if we look at this, that means we're only getting essentially 80% of basically that real power to the total amplitude of the instantaneous power that's being produced within the system. And obviously, because it was inductive, then we say 0.8 lagging. So 0.8 lagging. If it was a capacitor, we'd say 0.8 leading. We always have to say leading or lagging with the power factor, because it's the power factor that really tells us what type of system that we're actually working with. So we can actually do with less in terms of the information that we have within the system. Okay, so we don't want to have all this inefficiency. We want to bring down that reactive power Q. We want to get that thing down to maybe close to 0. And essentially, if we lower Q down to 0, then what we're creating is basically a system that has a power factor of what we call unity, or a power factor of 1. And if we have a power factor of 1, that means that we've essentially caused theta V minus theta I to be equal to 0, or, in other words, the two phase angles of the voltage and the current is actually just equal to 0. And so we know the cosine of 0 is equal to 1, or in this case, the ratio of real power to apparent power is actually just equal to 1, meaning that they're saying that we've taken those two phase angles of the current, we've caused both of those to come together, meaning that they're in phase, which means that we have a mostly or almost exactly a resistive system. I like saying mostly because we're still going to have an inductor in there, we're still going to have a capacitor, we're just going to cancel out the effect of both of them. So, how do we actually calculate the value of capacitance that we actually want to work with? Well, as before, we said Q corrected, and what we're going to correct by is 4650 var. So we're going to correct by that entire amount and divide that by omega and then also the magnitude of Vrms squared. So 4650 over 377 multiplied by 440 squared, and that comes out to be equal to 63.66 microfarads. And so now we actually have a capacitor that we can put in parallel here. So let's just go ahead and calculate the impedance for it. So ZC, obviously 1 over j omega c, and that came out to be equal to negative 41.67 ohms. But that answers the question, what capacitance value do we have that would actually do this correction for us and actually make our system more efficient? But we don't need to just take our calculation for granted and just say, yeah, that's what it is. We need to make sure that we know it works. So let's hook this thing back up in parallel and see if we actually did, in fact, lower down that power factor. Let's take a look at it. Sorry, increase our power factor to unity, lower down the reactive power. So here, 440 at an angle of 0 degrees, in parallel with 20 plus J15, and in parallel with minus J41.67. The equivalent impedance for here, take that 20 plus J15, put that in parallel with negative 41.67. That gave us 31.25 plus J0? How can that be? I don't know, guys. That's kind of weird. How can we actually have an inductor over here and a capacitor over here, but the equivalent impedance has no reactance in it? No, it doesn't. It definitely doesn't, because we actually calculate a value of capacitance that would basically create the reactance right here to go to 0. And sure enough, here S nu that we calculate is 440 squared over 31.25 minus J0, and the only thing that we have left within our system is 6200 volt amperes. Or we basically say that the system is basically providing all real power and is 100% efficient. 6200 watts is being delivered, but we really say 6200 plus J0 volt amperes. Congratulations, guys, we've created a fully efficient system. Alright, now what do we do if we say, well, single phase is kind of, well, that's just one phase that we can work with, but we generate 3 phases worth of basically current within a system generally. That's how we work within society. So that's what we're going to look at next.